Okay, guys, so in the last video, I lost connection, so I'm going to start over kind of right here on this example. So example one is where we'll start again. So I'm not sure how much of it recorded, so I'm just going to start from here. It says, find the mean number of home runs for the entire American League. Use correct notation. So once again, I'm going to use mu because it said for the entire American League, so that is the population. And I'm going to do 158 plus 136 plus 198. And then I'm going to add up all the teams, 195, and then I'm going to divide by 14. I'm just not going to write all of them out, but you guys should be adding each one of these, doing every single one. And then once you do that, you should end up with 179 home runs. Okay, so this is the average for the entire American League is 179 home runs. Okay, so now what we're going to do is we're going to find X bar. They say, suppose we take a simple random sample of 5 teams, the Red Sox, the Tigers, the Twins, the Yankees, and the Blue Jays, and we find the mean for these 5 teams. So this will be X bar now because we are using the sample and not the population, and we're finding the mean of the sample. So I'm just going to take, let's see here. The Red Sox had 198 home runs. The Tigers had 139. The Twins had 164. The Yankees, where are they at? Had 203. And who's the last team? The Blue Jays had 195. So I'm going to take all of these and I'm going to divide by 5. Okay. And I should get on my calculator 179.8 home runs. Okay, so when we took a simple random sample of 5 teams, we just randomly chose these 5, and you could do the same thing. You could randomly pick 5 teams. You could just get, 14 pieces of paper and put 1 through 14 on it, and then draw 5 numbers out of there, add those up, and divide by 5 and see if you get close to 179 as well. It says, what can you say about how representative the sample is in part B of all teams in the American League? It seems to represent the population of the American, oh boy, that's pretty ugly, American League. Well, because we got 179.8 and it was 179 for the entire population, that's pretty good. In this case, we do know the entire population's mean mu. In general, you will not know the entire population, but in these beginning chapters, we do some of the time. Okay, so the next thing we're going to talk about is the median. And the median is the midpoint or middle value of distribution, the number such that half of the observations are smaller and the other half are larger. The median is represented by M or as an X tilde. I'm normally just, if you're talking about the population, you use big M. If you're talking about the, actually, I've seen some books just use big M for the sample as well. So it really depends. In general, they're not as picky as when it's the mean. It says to find the median, arrange the observations in order from smallest to largest. If the number of observations is odd, then the median is the number located at the exact middle in the ordered list. If the number of observations is even, the median is the mean of the middle 2 observations in the ordered list. Note the formula location for the median is n plus 1 over 2 does not give the median itself, but rather just the location. So this is very important. We've already done problems like this in the previous chapter, in chapter 2. So we're going to be doing this again. And I want you to keep in mind, when you do n plus 1 divided by 2, that number is not the median. That's telling you that's the data value that is the median. So you have to decide what the data value is at that location in your list of numbers. So the first thing we have to do for this problem is we have to arrange it from smallest to biggest. So let's put these all in order. So let's see, what's the smallest? 0.42. What's the next smallest? 0.48. What do I got after that? 0.66, 0.73. Oops. What else we got? 1.10, 1.10, and then 5.40. I think that's right. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So now in order to find the location of the median, we do 7 plus 1 divided by 2. And this will give you the median location, okay? And this will be 8 over 2, which is 4. So now all I do is I go 1, 2, 3, 4. So this number right here is my median, okay? Hold on real quick. Okay, yeah, I had the wrong page on my notes. I was like, wait, that's wrong. So our median is 0.73. And notice there's 3 data values to the left of it, and there's 3 data values to the right of it. That was because there was an odd number. And it says right here, if the number of observations is odd, the median is located in the exact middle. If the number is even, we have to kind of do that averaging out thing that we had done of the 2 values that I did in the, I think it was like in the Hawaii problem from chapter 2. Okay, so it's pretty straightforward. Now notice this number 4 is not the median. That is the location of the median. It's the 4th number in the list. So the median is actually 0.73. Okay. Suppose the measurements of lead are replaced with these. So recalculate the median. So we're going to do 0.42, 0.48, 0.73, 1.10, 1.10, and 5.40. So now once again, there's only 6 values. So I'm going to do n plus 1 divided by 2. So this would be 7 over 2, which is 3.5. So the problem is you can't find the 3.5 number. So you have to find what's in between. So here's what we're going to do. Here's 1, oops, here's 1, 2, 3, and here's 1, 2, 3. So our median is somewhere right here, right? It's in this middle location right here. But we can't find it. So what we do is we are going to average it out. We're going to take 0.73. We're going to take 0.73 plus 1.10, and we're going to get 1.83, and then we're going to divide that by 2, okay? So I'm going to take out my calculator, and I'm going to do 0.73 plus 1.10 divided by 2, and I'm going to get 1.83 divided by 2, and I get 0.915. So now I know my median is 0.915. And that's this number right here. The number that would be right in between 0.73 and 1.10. Now again, notice because there was an even number, that means that we're going to have to average out the 2 values that are in that location, okay, or near that location. The median is not influenced by skew and outliers. It is resistant measure. It is a resistant measure, meaning not sensitive. The median is an appropriate measure of center for skewed distributions or distributions with outliers. So that's why I told you if a lot of people like don't take my exam, you know, the data is going to kind of be skewed. So, or there's going to be outliers. So what I do instead of using the average or the mean, I use the median to find like a good way to decide if I curve the exam. For this next problem, it says the following data refer to the weight gain in pounds of 10 women during pregnancy. Okay, so find the median. So once again, we have to write it in order. So I'm going to write it as, let me see here, 29, 30, 35, 36, 37, 39, 41, 46, oh, not 46, 43. Is there a 42 in there? 41, oh, another 41, sorry about that. 43 and 85. So 85 is definitely an outlier, so the median will be resistant to that. So when we go to find the median, we see that there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. So we're gonna have 10 plus 1. So let me erase that real quick. We're gonna have 10 plus 1 divided by 2. So this will be 5.5. So what I have to do is go 1, 2, 3, 4, 5, and 0.5. So I'm coming right here. So I'm going to do 37 plus 39 divided by 2 would be 38. So my median equals 38. Okay, maybe I should write that a little bit better. My median equals 38, okay, pounds. Okay, now my mean, I could just add all these values up on my calculator. So I'm going to just do 29 plus 30 plus 35 plus so on and so on and so on, all the way up to 85. And I'm going to divide it by 10. And I should get 41.6 pounds is equal to my mean. Okay, so our mean is actually equal to 41.61 pounds. Okay, compare the median and the mean. It looks like the median is going to be a little bit better of an estimation of the center of data, because if you look at the 41.6, the mean, remember the mean is trying to tell you where the center of the data is. The mean seems a bit off from the center, and here's why. The 85 is an outlier, right? It looks like an outlier, so it's bringing the mean way up. How many data values in our list are actually above 41.6? There's only two. There's 43 and 85, right? 41.6 is supposed to be the center of the data. Well, there's only two data values that are actually above it. That means that there is 8 data values that are actually below. So that doesn't feel very much like the center. However, if we look at the median of 38, here's 38 right here, 38's right here, right? So that means there's about, oops, I wrote it in the wrong chart. 38's right about here. So that means that there is about 5 to the left of it. There's about 5 to the right of it. Isn't that like what we would say is the center of the data? So the median in this case feels a lot more accurate to be the center of the data versus the mean, because the mean only has 2 data values above it and 7 data values below it, or 8 data values below it. So this is trying to demonstrate to you how the median is a little bit better indicator for the center of data if there is a skewness or there are outliers. So something I wanted to show you on the calculator, just give it a second. So you could actually use your calculator for this. I know you guys have a calculator with you. You may not have this emulator, which is fine, but you got to have a graphing calculator. So on your graphing calculator, you should go into Stat and Edit. And see this list 1 right here? So what we're going to do is we're just going to plug in the values from the table or from the list of data. 85, 41, 29, 39, 37, 41, 43, 30, 36, 35. Okay, and then you're going to get out of here. You're going to go second quit. So now you have entered in list 1, and notice I didn't put them in order because the calculator knows whatever list you give it, if it's trying to find the mean or median, it knows how to do it. It knows for the median, it has to be in order. So it already knows that. So now I'm going to go back into stat, and I'm going to go into calculate this time, and single variable stats. Use list 1, frequency list. Sometimes your calculator is just blank. So right there, do you guys see where it says X bar? Where it says X bar, it says 41.6, but wasn't that the mean that we found on our own when we did the calculation by hand? And then you guys see where it says, let me see here, let me scroll down a little bit on the calculator. See the median of 38? Isn't that the same answer that we got when we did it by hand by writing the list out and finding the middle value? So your calculator can find the mean and median very, very quickly just by going into stat and edit, entering in a list, and then going back into stat and calculate. So you can once again follow the instructions right here. Right here, there's a box in your notes that tells you how to do it on your calculator. Okay, so make sure that you know how to do this. This will save you time on the exams and on the homework as well. Comparing the mean and the median. So basically what they want you to do is to try to think about, like we just did, if we have a skew to the right. So let's say we have this graph right here, and the long tail on the right pulls the mean. So the mean is going to be a little bit further away from the center of the data because this table is, or the data is skewed to the right. So it's pulling the mean. The median is not affected by this skewness, so it gives us a better assessment of where the center of the data might be. Now, when you're dealing with perfectly symmetric normal distribution, like we have here, well, the mean and the median will be the same thing because it's perfect, okay? So that happens with normal distribution sometimes, if it's not approximately normal, but it's actually like perfectly normal distribution. But in general, if there's any skewness or outliers, you probably want to go with the median. And in general, if it's nice and symmetric, you probably want to go with the mean. Okay, so the mode is really easy. It's another way to talk about something. It says the value, or talk about center, but it's not, to me, it doesn't feel as accurate, but I know what they're trying to do. It says the value that occurs most frequently, and it's, I think when we use nominal data is a lot of time when we talk about the mode. The value that occurs most frequently, it can also be the category with the highest frequency. If the values occur with the same greatest frequency, there is more than one mode. If no value occurs more than any other value, there is no mode. So basically what this is saying is if there is a repeated value and it is the most repeated value, then that value becomes the mode. If there is a repeated value that, let's say, repeats itself 3 times, and then another repeated value or repeated outcome or a repeated data value that occurs the same amount of times as the other repeated one, then they are both the mode. Okay, now if no value occurs more often than another value, then there is no mode. So like if you had this, if you had 1, 2, 3, 4, 5, 6, 7, and I asked you what the mode is, you would say none, because all the values occur the equal amount of times, okay? But if we come over here and it says find the mode for the following data set, which data values occur most often? Well, we know the mode is the one that occurs most often. So we have, oops, I can just put equals. The mode is 27, and it is also 55. Because 55 occurs 3 times and 27 occurs 3 times. 88 and 99 don't occur as often as 55 and 27, so they're not part of the mode. Okay, the mode is very straightforward. Okay, the mid-range, the measure of center that is the value midway between the minimum, the smallest, and the maximum largest value of the data set. So if you ever want to find the mid-range, you just take the biggest value plus the smallest value and you divide by 2. The mid-range is very sensitive outliers, just very similar to the mean because it's accounting for the highest value and the lowest value. So what if the highest value is an outlier and the lowest value is an outlier? That's going to drastically affect what your mid-range is, and when in fact the data might not even be centered around that. So it says, let's see here, find the mid-range for this data set. Well, we know the lowest value is, or let's say the highest value, so the mid-range is 85 plus 30 divided by 2. So we do 85 plus 30 divided by 2, and we get 100. Now, does that feel like the mid-range for this problem when you think of the data sets? Oops, I think I did. Oh, no. Yeah, that's definitely wrong, guys. I forgot to use parentheses. 85 plus 30, enter, divided by 2 is 57.5. Sorry about that. But even that doesn't feel like the mid-range because the outlier of 85 is messing everything up. If you think about it, the mid-range is supposedly supposed to kind of tell you what's in the middle, midway between. But if you look at the data values, there's only one value bigger than 57.5, and that's 85. All the rest, the other 9 values are smaller than that. So compare the mid-range to the median. You calculate, is a mid-range an accurate measure of center for this data set? No, not at all. Because like I just said, oh wait, is there a smaller data value? Oh, there's a 29. I'm sorry about that, you guys. I didn't realize there was a 29 right here. So let's do 85 plus 29 divided by 2, and you should get 57 now. So 57 pounds. So no, it is not a accurate measure for center. It's way off from where the center of the data probably is. Okay. Let's see here. Mean from a frequency distribution. Okay, so let's see here. Oh yeah, so this is kind of a, so if you're given frequency distribution and there's intervals, that becomes a problem, because if you think about it, you don't actually know. So right here, it says the frequency distribution below describes the speed of drivers ticketed by police in a 30-mile-per-hour zone. Find the mean of the frequency distributions. So here's the problem. We have 25 people that got a ticket written between 42 and 45 miles per hour. But do you know specifically how fast each of those drivers was going? How many were going 42? How many were going 43? How many were going 44? How many were going 45? We don't actually know. The frequency table does not tell us that. So what we try to do with this is we try to use the midpoints to help us approximate what we think the mean is. So what we're going to do is we're going to take 42.5 and 45, and we are going to find the midpoints for each one of these categories. So we're going to find the midpoint. So we're going to do 45 and 42. So that would be what, 87 divided by 2 would be 43.5. Then the next one, 49 plus 46 divided by 2 would be 47.5. The next one, 51.5. The next one, 55.5. The next one, let's see here, 59.5. 58 plus 69 divided by 2. Wait. It's 59.5. Yep, that's good. Anyway, my calculator freaked out right now. I think it rounded off or something. I have to mess with the values. So here's what we do. This is how we can try to calculate. So it says find the mean of the frequency distribution. So normally, if we wanted to do this accurately, they should give us all 50 values, right? They should give us all 50 tickets, and then we could find the median and we could find the mean and everything like that. But they didn't give it give us this. They just gave us this frequency table. So the point of the midpoint, this midpoint idea, is it's saying, well, I don't know how many people were going 42, 43, 44, 45. So what I'm going to do is I'm going to guess that in general, most of the tickets, if we wanted to average things out, it's 43.5, okay? And how many people were going 43.5? There were 25 of them. So what I'm going to do is I'm going to say X bar equals 43.5 miles per hour times, times 25 people, okay? Plus 47.5 miles per hour times 14 people. So all I'm doing is I'm using the frequencies with the midpoints. 51.5 times 7 people plus 55.5 times 3 plus 59.5 times 1. And I'm going to divide all of that by 50 people, right? There were 50 tickets. So then X bar equals, so what I'm going to do is I'm going to do 43.5 times 27, or 25, sorry, plus 47.5 times 14 plus 51.5 times 7 plus 55.5 times 3 plus 59.5 times 1 divided by 50. I get 46.78. Okay, so 46.78 is the average speed of people ticketed in miles per hour. Okay, so that means on average, people were going about 46.78 miles per hour for this whole study of 50 people and their tickets. Okay, so that's what they were trying to do with this. Now that's finding the average. We can't really find the median because we need to know the actual numbers, the actual data values. We can't just average it out. But this is a way using this formula. And remember, this notation right here just means sum. This is sigma notation for sum or add things up. Okay, so don't let that you know, freak you out at all. That's just summation notation or sigma notation. Okay, let's see here. Weighted mean. This is something that some people do with like tests when they say like a final's worth 40% of your grade and a midterm's worth 30% of your grade. This is a weighted mean. So we can do this problem, and this shows us a similar formula for X bar. So it says you take the weight. So suppose you wish to find the mean score of 3 exams, but the exams are weighted differently. The scores are 85, 90, and 75 in order that they were taken. The first exam is worth 20%. So what the very first thing I'm going to do is I'm going to do 20% or 0.20 times 85 plus I'm going to do the second exam is 30%. I'm going to do 0.30 or 0.3, oops, times, what did I get on that exam? A 90%, okay? Plus the last exam is worth 50%, so 0.50 times 75, okay? Now the weird part is I'm going to divide this by 1 because 0.20 plus 0.30 plus 0.50, if you add all those up, that's 1, okay? If you did it the other way and you turned it, instead of saying 20%, you just left it as a 20, you would do 20 times 85, 30 times 90, 50 times 75, but then you would have to divide by 100. So when we do this, we get 81.5, okay? So your score in the class is an 81.5 based on these 3 tests. So that's your score in the course, okay? Does, hopefully that makes sense. Again, you could do it a different way. Instead of using 0.20 for 20%, you could just use 20, 30, and 50, but then you have to divide by 100, okay? So just keep that in mind because you're no longer using the percent version. All right. So 3.3, let me see how much further I want to go with this video. Oh yeah, I better go a little bit more. This is quite a long section. So for this next part right here, we have measure of variation or spread. Variation describes the dispersion or spread of the data. The measure of variation presented in this chapter are range, standard deviation, variance, and quartiles. So it depends on the way you look at things. I've seen a lot of people, they really care about variance, but only because it talks to them about standard deviation. So what I'm going to do most of the time is I'm going to focus on standard deviation, and variance will be something that we don't cover as much. But if you know standard deviation, then you know variance. And if you know variance, you know standard deviation. Okay. So the range is pretty straightforward. The difference between a maximum value and the minimum value. Okay. So it's very straightforward. You just take the biggest value in the problem, you take the smallest value in the problem, you subtract them, and then however far that was, we call that your range. The range is also highly influenced by outliers. Standard deviation is a measure that tells us the average variation of the sample data values from their mean. So standard deviation, called S, can be found by doing this. And there's a way we'll do it on our calculator, but I'm also going to show you how to do it by hand as well, okay? So finding standard deviation by hand, okay? So it says first you compute X bar, meaning the mean, then you subtract the mean from each of the values, and we get X minus X bar. Then you square each of these differences obtained from step 2. This produces X minus X bar quantity squared. You add all of the squares obtained from step 3. This value is the sum of these squares. And this is oftentimes sum of the squares. This is in other statistics books, they focus on that instead of actually doing it. And then divide by n minus 1, then take the square root. So here's what we're going to do. We're going to literally go through this step by step, and I'm going to show you guys how to do it. If I ever ask you guys to do this by hand, you know, you will do it this way. But a lot of the times after chapter 3, we'll do standard deviation on our calculator. And right here, as you can see, it even tells you you could do it on your calculator as well. So I'm going to show you both ways. So what I'm going to do is I'm going to compute the mean. So if I want to find the mean, I just do 1. So the mean is just 1. So X bar equals 1 plus 3 plus 14 divided by 3, right? So that should be 17, 18 divided by 3. So that'll be 6. So then it says, once you know X bar, subtract the mean from each value. So I'm going to do 1 minus 6, 3 minus 6, and 14 minus 6. Okay, that was step 2. So let's see, that gives me -5, -3, and 8. Then it says square each of the differences obtained from step 2. So now I'm going to square this, and this will become 25, this will become 9, and this will become 64. Then it says add all of those squares up. So I'm going to then do 25 plus 9 plus 64. And then it says divide that by n minus 1, and then take the square root. So n minus 1 would be 3 minus 1. So this would end up becoming 98 divided by 2, which is 49. Okay, now it says take the square root of this, and this would become 7. So for this particular problem, the standard deviation, S equals 7. Okay, and what that actually means is this is how far, so it says up here, we're going to do it much more in depth, is the measure that tells you the average variation of the sample data values from their mean. So basically, it's averaging things out, how far away data values are from their mean. The standard deviation is almost like you can think about it as how far are you willing to walk away from the mean to get a certain clump of data values. And then if you walk another standard deviation away, how many more data values can you get within that? So the standard deviation is a very powerful tool that we're going to use repeatedly in this course over and over and over again. Okay, so let me see, does it say, so then variance. Oh, by the way, you guys can use this on your calculator. You can go and do single var stats and you'll get the same thing as me. So what if I plug in my calculator? Let's see here. Let's clear this. Let's go stat. Let's go edit. Let's clear our list 1. Okay, and we're going to plug in 1, 3, 14. Okay, and now we're going to quit. We're going to go stat, single variable stats, and calculate, just like before. And notice, you see how it says X bar is 6? That's what we got. And then you see where it says this capital S and then the lowercase x, that is the standard deviation of the sample, okay? So when they tell you the standard deviation of that sample, you get 7, but that's the same number that we got. So you can use your calculator with the single variable stats button to find the mean and the median, and now you can also use it to find the standard deviation as well, okay? We can also find the standard deviation of population red sigma. You can do it this way as well. Let's see here, which is basically very similar. Now variance, variance of a set of observations is an average of the squares of the deviations of the observations from their mean, which is equal to the square of the standard deviations. So basically, if you know the standard deviation, all you have to do is square it. So in this problem, the standard deviation was 7. So then S squared equals variance, which is equal to 49. So it's kind of like the number before you square rooted it. So that's why if you know variance, you can always find the standard deviation by square rooting. If you know the standard deviation, then you can always square it to find the variance. Now, the reason some books focus on variance first is I personally feel like standard deviation is more important. But in order to get to the standard deviation in the formula, you had to find the variance first. Notice we had 49 before we had 7, right? So we had this 49, which would have been the variance, and then we ended up getting the standard deviation, which was 7. So basically, a lot of books focus on variance first because in order to get to standard deviation, you had to find the variance. Me personally, in general, I want to know standard deviation more than variance, okay? But they go hand in hand. If you know one, you know the other. And this is the relationship between them right here, okay, for sample and population. Properties of, standard deviation and variance, sensitive to outliers and skewness. Standard deviation is greater than or equal to 0. So standard deviation is always a positive number, but you can go left in the negative direction, but you just say that you're going to the left in standard deviation versus going to the right. Values that are very close together have a small standard deviation because they're clumped up. Remember, the standard deviation is how far you have to go to get a certain amount of the data. Values that are very far apart have a large standard deviation. And standard deviation has the same units as the original observation. Okay, so let's take a look at this problem. It says a dietitian obtains the amount of sugar in centigrams from 100 centigrams in each of 10 different cereals. The values are listed below: 3, 24, 30, so on and so on. Find the range, standard deviation, and variance for the given sample. So I do not want to do this one by hand because it's too many values. So what I'm going to do is I'm going to use my calculator. So I'm going to take out my calculator. Okay, I'm going to clear it. I'm going to go into Stat, Edit. I'm going to clean up my list 1, clear, and then go down arrow, and that will clear it. So now I'm going to enter this in: 3, 24, 30, 47, 43, 47, 43. And remember, you don't have to put it in order because the calculator already knows it if they're asking you to find the median. I think they're asking us for standard deviation and variance, so we don't need the median, but I just wanted to let you guys know. 47, 13, 44, 39. 2, 4, 6, 8, 10. So 10 values. So now we're going to quit and get out of here. Now we go back into stat and we calculate single variable stats. And now we have our X bar is 29.7. We have our S, which is 17.017 if we round off. So I'm going to come over here and I'm going to do my standard deviation is 17.017, rounding to 3 decimal places. And let's see here, it says the range. Well, we know the range, you take the biggest value minus the smallest value. So we're going to take the biggest, which is 47, minus the smallest, which is 3, and we should get 44. So our range is 44. And this is centigrams of sugar. And then the variance, remember the variance is whatever the standard deviation is squared. So I'm just going to do 17.017 squared on my calculator. So I'm going to do 17.017, squared, and I get 289.578. Okay, 289.578 centigrams squared. Okay, because when you take centigrams times centigrams, you get centigrams squared. Okay, so that would be the variance. And again, the standard deviation we got from the calculator. So is the standard deviation of the values likely to be a good estimate of the standard deviations of the amount of sugar in all cereals consumed by the population? So in general, this won't be on the exam, but in general, is the standard deviation of values likely to estimate the standard deviation of the amount of sugar in cereals consumed by the population in general? Tends to underestimate the population value. So I don't think I'm going to put this on test, though. This won't be a not on the exam. Okay, but if you wanted to, that's not something I'm super going to focus on, but that is in general the truth about the standard deviation of the sample versus the population. Then we have something called unusual values. Let me see if I want to stop the video here. 1, 2. Yeah, you know what, guys? I think that's good for video 1. We'll talk about unusual values in the next video that I make for chapter 3, part 2. Well, actually, it's kind of part 3. I butchered the beginning of the video. So for this chapter, I think there's one really short video for the intro, and then there'll be another 2 videos. But that's going to do it for today, guys. Thanks for watching the video, and I will see you in class.